Have you ever pondered the possibility of our sun transforming into a black hole? A fascinating thought, isn't it? But before we delve into that, let's understand what a black hole really is. A black hole is a celestial object with a gravitational pull so powerful, even light cannot escape from its grasp. It's like a cosmic vacuum cleaner sucking up everything in its path. But how does a star turn into this terrifying yet fascinating cosmic phenomenon? It all begins when a star exhausts its nuclear fuel. The energy output decreases, causing the star to shrink. This process is called gravitational collapse. Now, if the star is massive enough, it can undergo a spectacular explosion, called a supernova. This is where things get interesting. After the supernova, the core of the star collapses under its own gravity, forming a black hole. However, not all stars become black holes. Some are too small and instead turn into extremely dense structures known as neutron stars. Now back to our original question. Could our sun turn into a black hole? As awe-inspiring as that notion might be, it's not possible. You see, our sun is simply not massive enough. It would need to be about 20 times bigger to even consider going supernova, let alone forming a black hole. In the grand scheme of the cosmos, our sun is a lightweight. Its mass is just a tenth of what would be required to collapse into a neutron star, never mind a black hole. So while our sun's fate is sealed, a black hole is not in its future. It simply lacks the necessary mass to create that kind of cosmic drama. So in conclusion, while black holes are indeed a fascinating aspect of our universe, we need not worry about our sun turning into one. Despite its impressive size and brightness from our earthly perspective, in the grand cosmic scale, it's just not big enough to create such a powerful and mysterious entity. Enjoy the sunshine, folks, because our sun is going to stay exactly as it is for a good long while. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Ever wonder what happens when something enters a black hole? Well, it's quite the cosmic conundrum. Black holes are astronomical objects with a gravitational pull so immense that nothing can escape their clutches, not even light. This is what makes them black and invisible to the naked eye. At the heart of a black hole, we find the event horizon. This isn't a physical surface, but a point of no return in space. Once something crosses this boundary, it's checkmate. There's no coming back. The speed needed to escape goes beyond even the fastest known entity in the universe, light itself. So imagine a place where everything, from radiant light to matter, goes in, but never comes out. It's like the universe's best-kept secret, a cosmic one-way street leading to an unknown destination. With such fascinating features, black holes have intrigued astronomers for years, and they continue to reveal the extraordinary mysteries of our universe. Black holes were not always a known entity in the astronomical world. Astronomers and scientists had to first discover these enigmatic entities, and then, over time, classify them into different categories based on their mass. This discovery and classification process was not a simple one, and it required a deep understanding of the cosmos and the laws that govern it. The classification of black holes is primarily based on their mass. The supermassive black holes, having between 100,000 to billions of solar masses, are typically found lurking at the centers of most large galaxies, including our very own Milky Way. They are the heaviest of black holes, and their enormous size is still a mystery that baffles scientists. Next are the stellar mass black holes, which are smaller but still incredibly massive, with masses ranging from 3 to dozens of times that of the Sun. These black holes are scattered throughout the Milky Way galaxy, and they are typically formed when a massive star collapses under its own gravitational pull. And then there are the intermediate mass black holes, a class that falls somewhere between 100 and 10,000 solar masses. Astronomers had long suspected their existence, but the most compelling evidence was found only recently, in May of 2019, when gravitational waves from the merger of two stellar mass black holes were detected. However, regardless of their size, all black holes share one common feature: a gravitational pull so strong that nothing, not even light, can escape once it crosses the event horizon. This is the defining characteristic of a black hole and the reason behind their name. They are truly the darkest entities in the cosmos, absorbing everything that comes their way and giving nothing back. Thus, black holes can vary greatly in size, but all of them share the common feature of a gravitational pull so strong that nothing can escape. The study of these cosmic entities continues to be a fascinating field in astronomy, offering much to learn about the universe and our place within it. But how do these celestial behemoths come into existence, you may ask? Well, let's delve into the cosmic cradle of black holes. Stellar mass black holes, the smaller siblings in the black hole family, are born from the remnants of massive stars. Imagine a star that's more than 20 times the mass of our sun. This star lives a brilliant, fiery life until it exhausts its nuclear fuel. The core then collapses under its own gravitational weight, leading to a supernova explosion that blasts the outer layers of the star into space. This dramatic demise leaves behind a crushed core. If this core contains more mass than about 3 times that of the sun, no known force can halt its collapse into a black hole. Then we have the mysterious supermassive black holes, the enigmatic giants of the cosmos. These entities have been known to exist since the dawn of a galaxy's existence. Their origin, however, remains a tantalizing mystery. Some theories suggest they might be the result of hundreds or thousands of smaller black holes merging over billions of years. Others propose they could be primordial black holes, relics from the early universe. Once formed, black holes are not content just to sit quietly. They can grow by pulling in and absorbing material from their surroundings. Picture a greedy cosmic vacuum cleaner, sucking up gas from nearby stars, dust, other black holes, and any unfortunate celestial object that strays too close. This process is known as accretion, and it's one way a stellar mass black hole can grow into an intermediate or even a supermassive black hole. But that's not all. Black holes can also grow by colliding and merging with other black holes, creating a bigger, more massive black hole. Think of it as a cosmic dance where 2 black holes spiral in towards each other until they finally collide in a spectacular merger, sending ripples across the fabric of space-time. So, in a sense, black holes are the ultimate recyclers of the universe. In 2019, humans laid eyes on a black hole for the first time. This was a landmark in human history, a testament to our insatiable curiosity and unyielding spirit of exploration. Through the combined efforts of international scientists, we managed to capture the first image of a black hole using the Event Horizon Telescope, a network of 8 ground-based radio telescopes that effectively formed a single Earth-sized dish. The black hole image was no ordinary one. Known as M87, it's a supermassive black hole situated right at the heart of a galaxy more than 55 million light-years away. Its mass is staggering, clocking in at over 6 billion times the mass of our sun. That's a scale difficult to comprehend, but to give you an idea, its event horizon, the point of no return for anything that falls within its gravitational pull, is so vast it could engulf most of our solar system and even space beyond the planets. But what does the image show us? It's a dark circle, a void, surrounded by a disk of glowing hot matter. This is matter spiraling into the black hole, accelerated to ridiculous speeds, heated to extreme temperatures, and ultimately doomed to disappear beyond the event horizon. The darkness in the center is the black hole itself, a region of space where gravity is so strong that nothing, not even light, can escape. This image was a triumph, not just technologically but scientifically. It provided a direct visual confirmation of something we'd only known through equations and indirect observations. It turned a theoretical concept into a tangible reality. The photo of M87 is more than just an image. It's a reminder of our place in the universe, a symbol of human achievement, and a stepping stone to unraveling more cosmic mysteries. This significant achievement marked a new era in our understanding of these cosmic giants. It's a testament to our potential as a species, a beacon of hope in our pursuit of knowledge, and a promise of more amazing discoveries to come. Black holes also played a key role in confirming one of Albert Einstein's predictions. In 2015, a century after Einstein's general theory of relativity was published, scientists made a groundbreaking discovery that substantiated one of its major predictions: gravitational waves. These are ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. Einstein predicted that the collision of 2 black holes would create these waves, and over 100 years later, his theory was confirmed. The event that led to this discovery was named GW 150914. It involved the collision and merger of 2 black holes, an event so cataclysmic that it sent ripples through the very fabric of space-time. These ripples, akin to the way a stone tossed into a pond creates waves, traveled across the universe for 1.3 billion years before they were finally detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO is a marvel of scientific engineering. It uses laser beams to measure the minute changes in distance caused by passing gravitational waves. When the waves from GW 150914 reached Earth, they caused a change in distance of just 1,000th of the width of a proton. Yet, LIGO was able to detect this incredibly minute shift, confirming the existence of gravitational waves. Since that first detection, LIGO and other observatories like it have picked up more gravitational waves from other black hole mergers. Each of these events provides scientists with valuable insights into the nature of these enigmatic celestial objects. They allow us to study black holes in a way we never could before, giving us a means to test theories and further our understanding of the universe. The role of black holes in the discovery of gravitational waves is monumental. They've become cosmic laboratories, enabling us to study the extremes of physics. Their immense gravitational pull and the waves they produce when they merge are helping us unravel the mysteries of the cosmos. These observations have opened up a new way for us to study and understand the universe. Black holes, once just a theoretical concept, are now a tangible part of our understanding of the universe. We've journeyed through their discovery and classification, from the supermassive behemoths lurking in the hearts of galaxies to the stellar mass black holes scattered throughout the Milky Way, and the elusive intermediate mass black holes. We've delved into the cataclysmic formation of these cosmic entities, born from stars collapsing under their own weight and their ability to grow by absorbing the matter around them. We've even had the privilege of witnessing the first image of a black hole, a dark circle surrounded by a disk of glowing, hot matter. And let's not forget the groundbreaking detection of gravitational waves, a testament to the immense power of black holes and their role in shaping our understanding of space-time. As we continue to delve deeper into the mysteries of the universe, who knows what new secrets black holes will reveal? If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Isn't it intriguing to think about the paradox of black holes? Entities known for consuming light, yet they are capable of emitting it? Black holes, these enigmatic celestial entities, have a peculiar way of making their presence known. Their massive tidal forces heat up the surrounding matter to millions of degrees. This heated matter then emits radio waves and X-rays, an impressive spectacle from something known for its darkness. So, while light cannot escape a black hole's event horizon, these cosmic entities are not as dark as they might seem. Now, you might be asking, what happens to the matter that gets even closer to the event horizon? Well, let's delve into this cosmic spectacle. As some matter dares to orbit closer to the event horizon, the massive tidal forces of a black hole can fling it out. This creates jets of particles that, while traveling at nearly the speed of light, release radio, X, and gamma radiation. Quite the fireworks display, isn't it? But the spectacle doesn't end there. Think about supermassive black holes. Their jets can shoot out into space for hundreds of thousands of light years, painting a radiant picture against the cosmic canvas. Yes, even in their destructive power, black holes contribute to the spectacle of the cosmos. But why does it matter that black holes emit light? Well, we're so glad you asked. It's all about understanding the universe we live in. This phenomenon plays a crucial role in unfolding the mysteries of black holes and their surroundings. It's like peeling back the layers of an onion, revealing the inner workings of these celestial giants. This light emission also aids in the study of the formation and evolution of galaxies and the cosmos itself. NASA's Hubble, Chandra, Swift, NuSTAR, and NICER space telescopes, among others, are hard at work, measuring black holes and their surroundings, providing invaluable data for scientists worldwide. So, next time you gaze at the stars, remember, there's more to the cosmos than meets the eye, and black holes are a shining example of that. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. About our sun, have you ever pondered its future? What will unfold when its fuel supply diminishes? Let's delve deeper into this thought. As of now, our sun is powering itself by fusing hydrogen atoms in its core, a phenomenon shared by most stars. However, in approximately 5 billion years, it will deplete its hydrogen reserve. This factor will trigger the sun's. It's essential not to visualize this as an abrupt implosion, but rather as a transformation. As the core collapses, the sun will begin to fuse hydrogen in a shell surrounding this core. Concurrently, the core will initiate the fusion of heavier elements. The outcome? A surge in the sun's heat production, causing the sun's outer layers to expand into space, potentially so far as to swallow Earth, thereby making it unsuitable for life as we know it. So the sun is destined to morph into a red giant, an era that will span about 1 billion years. But what transpires after that? After the red giant phase, the sun will reach its final stage. But what does this mean for our star? Well, the sun's grand finale is quite a spectacle. After spending about 1 billion years as a red giant, our sun will undergo a transformation, collapsing into a white dwarf. Imagine a star, once a fiery, luminous ball of gas, now a tiny, dense remnant. But don't let the term dwarf mislead you. Despite its small size, a white dwarf is incredibly dense and continues to glow from residual heat. It's like the ember of a once roaring fire, still holding on to its warmth long after the flames have died out. This transformation, however, won't be happening anytime soon. We're looking at a timeline of about 6 billion years, and though it might sound like a somber end, it's actually a rather beautiful one. So our sun's story isn't over yet, but when it is, it will leave behind a glowing testament to its former glory, a white dwarf. If you want to keep up to date and get notified when we release new videos, click on like and subscribe. This helps us keep the channel going and lets us know that you're enjoying our content. Ever wondered about the life cycle of a star? What happens when a star like our sun exhausts its nuclear fuel? Well, let's dive into the fascinating world of astronomy to find out. Stars, those twinkling points of light scattered across the night sky, are cosmic powerhouses burning nuclear fuel to radiate light and heat. But like all things, their fuel is finite. When a star exhausts its nuclear fuel, it undergoes a spectacular change. It sheds its outer layers in a cosmic spectacle, leaving behind a hot core. This core, bereft of its outer layers, cools down over an unimaginably long period of time, spanning billions of years. The result? A white dwarf, a compact and incredibly dense object that is, in essence, the remnant of a star. Despite its name, a white dwarf is anything but dull. It's a testament to the resilience of matter and the unending cycle of cosmic life and death. This is how a white dwarf comes into existence, marking the final stages of a star's life. So, what is a white dwarf made of? The answer lies in understanding degenerate matter. In a white dwarf, the energy released from fusion ceases, and this lack of internal pressure allows gravity to compress matter inward. This compression is so intense that even the electrons within the star's atoms collide. Typically, electrons, being identical in spin, cannot occupy the same energy level. You see, only 2 electrons can share an energy level due to the 2 possible directions an electron can spin. This concept is known in physics as the Pauli exclusion principle. In a regular gas, this isn't a problem. Why? Because there aren't enough electrons to fill each energy level completely. However, a white dwarf is different. Its density is significantly higher, and its electron population is much more tightly packed. This results in a gas known as degenerate, meaning that all of the energy levels within its atoms are filled with electrons. Gravity has to push electrons into spaces they can't occupy to compress the white dwarf further. But here's the catch. Once a star is degenerate, gravity can't compress it any further. Why? Because quantum mechanics states that there's no more room left to occupy. So it's the quantum mechanical principles, not internal fusion, that keep our white dwarf from collapsing. Also, a white dwarf has some strange characteristics. For example, as its mass increases, it actually shrinks in size. This is because the star's electrons have to squeeze closer together to maintain enough outward pressure to support its added mass. However, there's a limit to the amount of mass a white dwarf can have. This limit, discovered by Subrahmanyan Chandrasekhar, is 1.4 times the mass of the Sun, and is aptly named the Chandrasekhar limit. A white dwarf's surface gravity is 100,000 times greater than Earth's. This intense gravity means that lighter atoms float at the surface, while heavier ones sink in its atmosphere. In some white dwarfs, the atmospheres are almost pure hydrogen and helium, the lightest elements. It is the quantum mechanical principles, not internal fusion, that keep our white dwarf from collapsing. A white dwarf is not your ordinary celestial object. It has some unique characteristics. Let's start with its size. Unlike most objects in the universe, a white dwarf gets smaller as its mass increases. This is because the electrons within a white dwarf must compress closer together to maintain enough external pressure to support its greater mass. It's a bit like trying to fit more and more people into an elevator. As the number of people increases, everyone has to squeeze in tighter. Now, there's a limit to how much mass a white dwarf can have. This maximum mass, discovered by Subrahmanyan Chandrasekhar, is 1.4 times the mass of the Sun. This is known as the Chandrasekhar limit. If a white dwarf's mass exceeds this limit, it can no longer support its own weight and will collapse, possibly triggering a supernova explosion. Next, let's look at the surface gravity of a white dwarf. It's a staggering 100,000 times greater than that of Earth. This extreme gravity affects the white dwarf's atmosphere in peculiar ways. For instance, lighter atoms float to the surface, while heavier ones sink. In some white dwarfs, the atmospheres are almost pure hydrogen or helium, the lightest elements in the universe. This immense gravity also pulls the atmosphere close to the white dwarf. To give you an idea of how close, if this happened on Earth, the top of the atmosphere would be below the peaks of our tallest skyscrapers. These are just a few of the peculiar characteristics of a white dwarf. Each one of these traits, from the way it shrinks as it gains mass, to its extreme surface gravity, to the purity of its atmosphere, makes a white dwarf a unique and fascinating celestial object. These peculiar characteristics make a white dwarf one of the most intriguing objects in the universe. Beneath the atmosphere of a white dwarf lies an interesting crust. Just as the crust of our Earth holds many secrets, so does the crust of a white dwarf. It's thought to be 50 kilometers thick, a substantial layer in the grand scheme of these celestial bodies. But what makes this crust truly unique is its composition. It's made up of a crystalline lattice of oxygen and carbon atoms. These atoms, under the immense pressure and temperature of the star, solidify into a structure similar to that of a crystal. Now, let's take a moment to make a fascinating comparison. A cool carbon and oxygen white dwarf shares quite a few characteristics with a diamond. Yes, you heard that right. A diamond, one of the most sought-after gemstones here on Earth. Both contain carbon atoms arranged in a crystalline lattice. So, in essence, a white dwarf could be considered a celestial diamond. Just imagine, a diamond sparkling in the vast expanse of our universe. Why should we care about white dwarfs, you might ask? Well, the importance of these celestial bodies cannot be overstated. White dwarfs serve as cosmic timekeepers. Their predictable cooling rates allow astronomers to estimate their ages, hence providing a unique insight into the history and evolution of our galaxy. Moreover, the study of white dwarfs can provide profound insights into the life cycle of stars. Observing white dwarfs helps us understand the ultimate fate of our own sun, which is expected to become a white dwarf in about 5 billion years. White dwarfs also play a crucial role in the formation of heavy elements. When they explode as type Ia supernovae, they spew out elements like iron, seeding the cosmos with the building blocks for new stars, planets, and even life. So, in the grand scheme of the cosmos, understanding white dwarfs is key to unraveling the mysteries of the universe. Do you believe there is a better way for us to use the energy that our sun produces? We mean more sophisticated means of obtaining the energy we require, not solar paneling. Please share any suggestions you may have for obtaining energy from our very own solar nuclear power plant so that we can power our future.